June 23, 1942. 4:10 a.m. The docks of Akron, Ohio are silent except for the hollow rattle of an empty freight car. A crane swings slowly over stacked crates that should be filled with rubber, but aren't. Workers stand in clusters, hands in pockets, staring at manifests stamped in red ink, delayed, cancelled, unavailable. You can almost smell it, hot metal, stale oil, and something else. Absence. Inside a dimly lit warehouse, a factory supervisor runs his hand across a conveyor belt that isn't moving. The rubberized surface is already cracking. Machines built to run day and night are quiet. Tires for bombers, gaskets for tanks, insulation for wiring. Everything that moves in war depends on one material that no longer exists in reliable supply. Across the Pacific, ships carrying natural rubber have stopped coming. Not slowed. Not delayed. Stopped. Because in a matter of months, Japan seized nearly every major rubber-producing region in Southeast Asia. Plantations that once fed global industry now served a different empire. Supply lines vanished behind advancing armies. Warehouses emptied faster than anyone believed possible. And in Washington, D.C., the realization arrived like a silent detonation. Rubber wasn't just a commodity. It was mobility. Without it, trucks could not roll, aircraft could not land, tanks could not move, radios could not function, and war could not continue. At 9:02 a.m., inside a federal office heavy with cigarette smoke, a man unfolded a report and read a number twice to be sure he understood it. The United States possessed barely enough natural rubber to sustain operations for 1 year. 1 year, if rationing was immediate and absolute. He removed his glasses, rubbed his eyes, then read the final line. No existing substitute production capacity. No backup. No reserve plan. No hidden stockpile. Just a countdown. Across the industrial heartland of the United States, factories that had transformed overnight into engines of war were about to face a new enemy, not a nation, but a missing material. In Detroit, assembly lines still produced tanks, but engineers quietly reduced training mileage to preserve tires. In California, aircraft crews inspected worn landing gear with growing unease. In Pennsylvania, train operators logged maintenance delays because rubber seals could not be replaced. It didn't happen all at once. It happened in small, unsettling signs. Cracks where there should be flexibility. Leaks where there should be pressure. Friction where there should be motion. War machines built for unstoppable momentum began to feel fragile. And fragility in wartime spreads faster than fear. At a refinery office overlooking miles of smokestacks, a tall, methodical industrialist reviewed emergency proposals. He was not a chemist by training. He was not a general. He was something else, a coordinator of vast systems, a man accustomed to impossible scales. His name was William M. Jeffers. Until that moment, his career had been measured in railroads and fuel distribution, logistics, movement, infrastructure. Now he faced a different challenge, creating an entire material industry from nothing. Not improving production, inventing it. Jeffers did not dramatize the crisis. He asked one question: how much synthetic rubber can we produce today? The answer came quietly: almost none. A pause followed, long enough for the weight of reality to settle into the room. Then he asked a second question: how fast can that change? No one answered immediately, because the truth was simple and terrifying. Synthetic rubber existed only in limited laboratory forms, small batches, experimental formulas. No national-scale manufacturing, no unified process, no supply chain, no time. But war has a way of compressing what is considered impossible. Jeffers didn't argue. He didn't debate feasibility. He didn't request more studies. He made a decision. The nation would not search for rubber. It would create it. Within days, emergency meetings drew together rival corporations that normally competed fiercely for patents and profits. Chemical companies, oil producers, engineers, military procurement officers. Men who had never shared trade secrets were now required to share everything. Maps were spread across tables showing refinery locations, transportation lines, and potential factory sites. Chalkboards filled with chemical formulas few military officers understood. Production estimates fluctuated wildly depending on raw material availability. Every conversation circled the same obstacle: scale. Creating synthetic rubber in a lab was one challenge. Creating enough for an army was something entirely different. It required raw materials, reactors, catalysts, pipelines, power grids, trained workers, and transportation networks, all built simultaneously. The timeline was measured not in years, but in months. And every delay meant fewer vehicles on battlefields that stretched across continents. Back in Akron, a tire plant manager conducted a demonstration for visiting officials. He held up 2 strips of material. One natural rubber. One experimental synthetic sample. The natural rubber bent smoothly, returning to shape instantly. The synthetic strip cracked slightly at the fold. Silence filled the room. This was the gap they had to close, not gradually, but immediately. Quality mattered. Durability mattered. War would expose weaknesses brutally. A tire that fails during a landing. A seal that fails in a submarine. A gasket that fails inside an engine at full load. Failure in materials becomes failure in machines. Failure in machines becomes failure in missions. Failure in missions becomes something far more permanent. Jeffers began assembling something unprecedented. Not a single factory, but a national network designed to function as one coordinated organism. Oil refineries would supply raw hydrocarbons. Chemical plants would process intermediates. New facilities would polymerize compounds into rubber substitutes. Transportation corridors would link them into continuous flow. It wasn't a factory system. It was an industrial ecosystem. And it had to function without precedent, without trial periods, and without margin for error. He moved quickly, often before full plans existed. Construction contracts were issued while blueprints were still being revised. Equipment was ordered before final processes were fully standardized. Speed was not a goal. Speed was survival. Meanwhile, public life shifted quietly to support the crisis. Civilian rubber drives collected worn tires, raincoats, even old garden hoses. Children brought scrap to school collection points. Newspapers printed diagrams showing how to conserve tire usage. To the public, it was framed as patriotic contribution. Behind closed doors, it was necessity, because every pound salvaged extended the window of time in which a solution could emerge. Late one evening, Jeffers walked through a partially completed synthetic rubber plant. The structure was skeletal, exposed beams, unfinished piping, workers installing reactors under temporary lighting. He paused beside a massive vessel that would soon host chemical reactions at industrial scale. The metal surface was cold, unproven. He knew what critics were whispering. That chemistry could not be forced into mass production so quickly. That quality would suffer. That resources might be wasted chasing an illusion. But he also understood something others had not yet fully grasped. This was not the manufacturing project. This was a race against strategic paralysis. If vehicles could not move, battles could not be fought. If battles could not be fought, alliances could fracture. If alliances fractured, the war's balance would tilt permanently. Rubber was not just material. It was momentum. By autumn of 1942, dozens of plants were under construction simultaneously. Engineers worked around the clock solving problems that had never existed at this scale: pressure instability, catalyst contamination, polymer consistency. Sometimes reactors failed catastrophically during testing. Sometimes entire batches were unusable. Each failure consumed time the nation did not possess. Yet progress continued. Small flows became measurable output. Measurable output became scheduled production. But one question lingered in every strategic meeting. Would it be enough? Because while factories rose in America's interior, battlefields expanded overseas. Armies moved across deserts, jungles, and oceans, consuming rubber faster than any peacetime economy could imagine. Production was climbing. Demand was accelerating faster. In December 1942, a confidential briefing summarized the situation bluntly. If synthetic output does not reach full scale within 12 months, operational mobility will decline across multiple theaters. No embellishment. No rhetoric. Just a timeline narrowing toward crisis. Jeffers read the report without visible reaction. Then he turned to the engineers and asked for revised output projections. Not hopeful estimates. Real ones. The numbers were staggering, if achieved. But they depended on something fragile. A single chemical pathway that had never been proven under continuous national-scale demand. If it worked, supply would stabilize. If it failed, the war machine would begin to slow, visibly. And once momentum in war begins to slow, recovery is never guaranteed. Winters settled across industrial America. Snow collected on unfinished plant roofs. Steam rose from test reactors operating through the night. Workers rotated in exhausting shifts, many aware only that they were building something vital, not yet knowing how decisive it would become. Inside one control room, a gauge needle trembled, then steadied. A technician leaned closer, flow rate increasing. Slightly, but steadily. Synthetic rubber, not in experimental grams, but in industrial volume, had begun to move through the system. A thin stream, fragile, uncertain, but real. And if that flow could be sustained, everything would change. But could it survive the pressure of total war? The control room lights hummed softly as gauges climbed out of the red. January 14, 1943. 2:37 a.m. A technician wiped condensation from a glass viewport and leaned in, breath fogging the surface. Inside the reactor, a pale, viscous substance churned in slow rotation. Not smoke, not vapor, something heavier, something forming. You can almost hear the subtle rhythm of valves opening and closing, like a mechanical heartbeat learning to live. For months, Chemist had wrestled with instability, reactions that stalled without warning, polymers that hardened too soon, catalysts that lost potency after hours instead of days. Now, for the first time, the process was not collapsing under scale. It was holding. And if it held long enough, synthetic rubber would cease to be an experiment. It would become infrastructure. In laboratories tied directly to new production plants, teams refined a method based on petroleum-derived chemicals. Instead of relying on tree sap harvested in tropical climates, this process began with hydrocarbons extracted from oil. The raw material was abundant, domestic, and, most importantly, controllable. The challenge wasn't simply to make rubber-like material. It was to make a product that could endure stress at high speed, under heat, across thousands of miles of motion. Tires on a bomber landing at full weight. Tank treads grinding over fractured terrain. Seals inside engines vibrating for hours without pause. If the chemistry failed, everything built upon it would fail too. Supervisors paced catwalks overlooking rows of reactors, towering cylinders wrapped in pipes that pulsed with heat and pressure. Workers in heavy gloves adjusted valves with cautious precision. Every change in temperature, every shift in pressure, could alter the final structure of the polymer chain. And structure determined strength. Too rigid, and the material would crack under stress. Too soft, and it would deform beyond recovery. Perfect balance was not a luxury. It was survival engineered at the molecular level. Some nights, production stalled without clear cause. Operators would shut down a line, disassemble components, and discover contamination invisible to the eye, a trace impurity enough to disrupt the entire reaction. Each failure was studied, recorded, corrected, and fed back into the system. War had transformed chemistry into a battlefield of equations. At the center of coordination stood William M. Jeffers, moving between factories, refineries, and federal offices with relentless focus. He demanded standardization across companies that had never cooperated before. Processes had to match. Measurements had to align. Output had to become predictable. Rivalries dissolved under pressure of necessity. Patents were shared. Techniques exchanged. Engineers who once guarded secrets now taught one another how to prevent catastrophic failure inside reactors the size of buildings. It was not collaboration by choice. It was collaboration enforced by time. Raw materials began arriving in steady convoys. Tank cars carried feedstock from refineries. Pipelines fed intermediate chemicals directly into processing plants. Rail lines that once transported consumer goods now moved components for a single objective: sustained synthetic production. Across the United States, a quiet transformation unfolded. Entire regions reorganized around a material that had not existed at scale 1 year earlier. New towns formed around plants. Shift whistles replaced church bells as the dominant rhythm of daily life. Workers measured time not by calendar dates, but by production quotas. The nation had not simply responded to shortage. It had reorganized itself around replacement. Meanwhile, military planners watched closely. Reports from overseas were growing more urgent. Tire wear rates in desert campaigns exceeded projections. Aircraft maintenance crews logged increasing concern over supply reserves. Transport divisions recalculated movement schedules based on remaining material lifespan. Mobility, the defining advantage of modern warfare, hovered on a narrow margin. Every pound produced in these new plants translated directly into miles of movement on distant battlefields. And movement determined initiative. One afternoon, an inspection team observed a continuous production run surpassing all previous output levels. The material emerging from the process displayed elasticity comparable to natural rubber. Not identical, but close enough for deployment. Close enough for war. Test engineers cut strips, stretched them, heated them, stressed them under load. The results held. For the first time, planners authorized expanded integration into military manufacturing. Synthetic rubber was no longer a contingency. It was becoming supply. Yet success revealed a new problem. Volume. Producing rubber in batches was no longer sufficient. Demand required uninterrupted flow day and night, without pause, across dozens of facilities operating in synchrony. Any disruption in one plant could cascade through the network, reducing output everywhere. The system had grown powerful, but also fragile. Late winter storms swept across industrial regions, freezing pipes and halting transport lines. Engineers worked through the night insulating systems, rerouting flows, preventing shutdowns that could erase weeks of progress. You can almost feel the cold biting through gloves as workers hammered ice from valves at dawn. War did not pause for weather. Neither could production. By early spring of 1943, output graphs began rising at a pace few had predicted possible. Numbers that once represented goals now represented minimum expectations. Plants that had struggled to stabilize reactions were now refining efficiency. But deep inside planning offices, analysts saw a different truth hidden behind the rising curves. Demand was still increasing faster. The war machine was expanding. More vehicles, more aircraft, more movement across greater distances. Synthetic rubber had begun to flow. But could it flow fast enough to keep pace with a global war accelerating toward its most decisive phase? And as production scaled upward, a new question emerged, one not of chemistry, but of consequence. What would happen when synthetic rubber finally reached the front lines? July 3, 1943, 6:12 a.m. A transport convoy idles on a dusty airfield in North Africa. Heat already shimmers above the runway, though the sun has barely risen. Mechanics crouch beside a heavy truck, pressing their thumbs into the sidewall of a newly mounted tire. The surface feels different, slightly firmer, less forgiving. Synthetic. No ceremony marks the moment. No announcement. Just a quiet nod from a supply officer and a signal to move. Engines roar to life. The convoy begins to roll. You can almost feel the tension in every vibration as those tires touch the earth for the first operational miles of a material born from emergency. Across multiple theaters, the first shipments arrived with little fanfare. Crates stamped with procurement codes replaced dwindling reserves of natural rubber components. Maintenance crews examined them with cautious skepticism. Would they hold under stress? Would they fracture under heat? Would they survive the punishment of real war? Testing in laboratories had proven durability. Testing in motion would prove destiny. Aircraft ground crews installed synthetic rubber seals into hydraulic systems. Tank mechanics replaced worn gaskets. Supply units issued tires built from petroleum chemistry rather than tropical plantations. The transformation was subtle but profound. A supply chain severed by conquest had been replaced by one built from domestic industry. War planners began recalculating mobility projections. For the first time since the crisis began, those projections did not trend downward. Inside a forward maintenance depot, a technician logged performance data from vehicles fitted with synthetic tires. Mileage exceeded expectations. Heat resistance remained stable. Wear patterns differed slightly, but not catastrophically. He underlined one phrase in the report: operationally acceptable. In wartime language, acceptable meant revolutionary. Back in the industrial heartland of the United States, production plants had moved beyond stabilization into relentless expansion. Additional reactors came online. Efficiency improved. Output that once seemed miraculous became routine. Pipelines pulsed continuously. Railcars departed on strict schedules. Chemical feedstocks flowed in measured precision from refinery to reactor to finishing line. An ecosystem of motion had been born from absence. At Coordination Headquarters, William M. Jeffers reviewed distribution charts mapping synthetic rubber output to military demand. Red lines representing shortages began to shrink. Some disappeared entirely. But Jeffers was not celebrating. He was watching a different metric: sustainability. Could production maintain pace not for weeks, but for years? Because wars are not won by bursts of innovation. They are won by endurance. The psychological shift among planners was gradual but unmistakable. Previously, every decision carried the shadow of limitation. Now, possibility returned to strategic conversation. Transport units scheduled longer operations. Airfields expanded sortie rates. Armored divisions increased training mobility. Movement had regained confidence. And confidence in war changes behavior. Yet not all doubts had vanished. Reports from extreme climates, Arctic cold, desert heat, jungle humidity, revealed variations in performance. Engineers responded immediately, adjusting formulations, refining processes, tailoring production to operational conditions. Synthetic rubber was not a static invention. It was evolving in real time, shaped by the environments of global conflict. One evening in a testing facility, engineers subjected a synthetic tire to punishing conditions: rapid acceleration, heavy load, sustained heat. The material held longer than predicted. When it finally failed, it did so gradually rather than catastrophically. Failure had become manageable. And manageable failure is the foundation of reliability. Military supply officers began requesting increased allocations not as emergency substitution, but as standard issue. The transition from replacement to preference had begun. What was once a desperate experiment was becoming a pillar of logistics. But beneath this success, a larger realization was forming, one that extended beyond material science. If a nation could rebuild a critical resource entirely within its own borders, what other limitations could be erased? Production forecasts for late 1943 projected output levels that would not merely sustain operations, but enable expansion. The war machine would not slow. It would accelerate. An acceleration changes the balance of power more decisively than any single battle. Somewhere within strategic planning circles, a quiet conclusion emerged. The material crisis that threatened to paralyze Allied movement had instead triggered an industrial transformation. But transformation always carries consequences. Because when one side solves a problem thought unsolvable, the war itself begins to shift. And that shift was about to become visible on battlefields far from the factories that made it possible. November 18, 1943. 9:40 p.m. A bomber squadron prepares for takeoff from an English airfield. Ground crews move quickly beneath the wings, their flashlights cutting through mist and exhaust. A mechanic tightens the last fitting on a landing gear assembly, then presses a gloved hand against a tire surface still warm from testing. Synthetic rubber. He steps back. The aircraft begins to taxi. You can almost feel the vibration through the cold night air as weight settles onto material that did not exist at this scale a year earlier. Across the European theater, movement was increasing, not dramatically, not suddenly, but persistently. Convoys traveled farther without interruption. Aircraft maintenance cycles shortened. Vehicles once sidelined for lack of replacement components returned to service. Mobility had stopped shrinking. It had begun to grow. Strategists tracking operational readiness noticed a subtle but decisive shift. Equipment availability rates rose. Supply lines extended deeper. Armies could plan not only for survival, but for advance. Material abundance had not been restored. It had been reinvented. Reports filtered back through Allied command structures detailing improved logistical stability. Transport divisions recorded fewer delays tied to tire failure. Maintenance depots documented consistent availability of seals, hoses, and vibration-dampening components. It wasn't dramatic. It was dependable. And dependability is what allows strategy to become action. Within planning circles across the United Kingdom, operational proposals that once seemed too risky began to reappear. Expanded ground movement, sustained air campaigns, extended supply corridors across difficult terrain. Not because battles had changed, because materials had. Factories in North America continued their relentless output. Production lines that once struggled to maintain stability now operated with measured precision. Improvements in catalysts, temperature control, and polymer consistency transformed emergency manufacturing into industrial routine. Workers who had learned under pressure were now masters of a new craft. They could read subtle changes in flow by sound alone. They understood the rhythm of the process, the way seasoned sailors read wind and tide. Synthetic rubber was no longer fragile. It was predictable. Military planners began to grasp the deeper implication. The seizure of natural rubber sources by Japan had been intended to cripple Allied mobility. Instead, it had forced an industrial adaptation that removed dependence entirely. A vulnerability had been converted into resilience. And resilience in war compounds over time. On a rain-soaked supply road in Italy, a column of armored vehicles advanced steadily through mud that would once have halted movement. Tires gripped. Seals held. Engines sustained pressure without failure. No one in the convoy spoke about chemistry or production networks. They only felt the result, uninterrupted motion. Sometimes the most decisive transformations in war are invisible to those experiencing them. They are felt as continuity, as reliability, as the absence of breakdown. Back in strategic planning rooms, charts comparing material consumption to production capacity revealed something unprecedented. Supply was no longer chasing demand. It was beginning to exceed it. The implication was profound. Equipment could be used harder, longer, more aggressively. Operational tempo could increase without fear of material exhaustion. Momentum, once threatened, had returned with greater strength. Yet the transformation extended beyond logistics. It altered perception. Allied commanders began to understand that industrial adaptation could neutralize strategic surprise. Resource denial, once a decisive weapon, could be countered through innovation at scale. War was no longer only a contest of territory or tactics. It was a contest of systems. And one system had proven capable of rebuilding itself under extreme pressure. Inside planning headquarters, analysts traced the chain of cause and effect backward, from improved battlefield mobility to factory output, from factory output to coordinated industrial policy, from policy to a single decision to attempt what had never been attempted before. A decision to manufacture independence from nature itself. But a deeper realization was forming, one not limited to the current conflict. If industrial systems could create substitutes for essential resources under crisis conditions, then the limits of warfare were no longer defined solely by geography. They were defined by imagination. And imagination, once proven effective, does not retreat. By early 1944, Allied operations were preparing for actions that demanded enormous logistical confidence. Movements requiring sustained supply, rapid repair, and uninterrupted mechanical reliability. Plans that would have been impossible under the shadow of material scarcity. The war machine had not simply been repaired. It had been re-engineered. And the full consequence of that transformation was about to be revealed, not in factories, but in the scale of operations those factories now made possible. June 5, 1944. 11:58 p.m. The English Channel is black glass under a moonless sky. Engines rumble low across hundreds of vessels waiting just beyond the horizon. On crowded decks, soldiers check straps, tighten gloves, and sit in silence beside vehicles lined wheel to wheel. Every tire carries weight beyond steel and rubber. You can almost feel the tension in the air, not fear alone, but anticipation of movement on a scale never before attempted. In command headquarters, planners review final readiness reports for Normandy. One category stands out with quiet significance: material mobility readiness, sustained. 2 years earlier, that phrase would have been impossible. Behind every landing craft waiting in darkness stood a supply network that could replace wares quickly as war consumed it. Tires, seals, insulation, shock absorbers, components once rationed with caution were now integrated into massive logistical projections. This was not abundance for comfort. It was abundance for momentum. Commanders could plan operations assuming machines would continue moving day after day, week after week. Mechanical reliability had shifted from uncertainty to expectation. And expectation changes the scale of strategy. Inside a briefing room, Supreme Commander Dwight D. Eisenhower studied maps covered in colored lines representing movement corridors, supply routes, and reinforcement schedules. Every line depended on mobility: trucks advancing inland, aircraft rotating continuously, armored units pushing beyond initial objectives. Those movements were not sustained by heroism alone. They were sustained by material certainty. The ability to keep moving after landing was as critical as the landing itself. Across staging areas, mechanics performed final inspections. A young technician pressed a thumb against a tire tread and watched it rebound slowly to shape. No cracks, no weakness, no hesitation. He moved to the next vehicle, repeating the motion instinctively. Reliability had become tactile. You could feel it under your hand. When dawn broke over the invasion fleet, engines roared to life in coordinated sequence. Vehicles rolled forward, disembarked, advanced across terrain scarred by resistance and weather. They did not stop because of material failure. They did not pause because replacement parts were unavailable. They moved, continuously, relentlessly, because an industrial solution conceived in crisis had matured into strategic power. Synthetic rubber was not visible on the battlefield. Its presence was measured in uninterrupted motion. As Allied forces established footholds and expanded inland, supply lines extended with them. Trucks traveled long routes over damaged infrastructure. Aircraft landed repeatedly on hastily prepared runways. Armored units maneuvered through terrain that punished mechanical systems. Yet maintenance reports revealed a pattern few outside logistics circles fully understood. Failure rates were stable. Operational tempo remained high. Movement persisted. The war machine was not straining under demand. It was sustaining it. In industrial centers thousands of miles away, production continued without pause. Facilities that once raced against collapse were now supporting expansion. Output flowed not as emergency relief, but as strategic foundation. The transformation had reached maturity. A nation had learned not only how to replace a critical resource, but how to outgrow the limitations that resource once imposed. Historians would later measure battles and divisions and territories gained. But beneath those visible outcomes lay an invisible continuity. The capacity to move, repair, replace, and continue without interruption. War had entered a new phase where endurance itself became a weapon. And endurance is built not in moments of victory, but in systems that do not fail under pressure. By late 1944, Allied operations spanned continents with sustained mechanical reliability once thought unattainable under wartime strain. Mobility no longer fluctuated with resource access. It persisted regardless of geographic constraint. A vulnerability that once threatened paralysis had been transformed into strategic independence. But the full meaning of that transformation was not yet complete, because the achievement did more than sustain a war. It reshaped how nations understood the relationship between industry and survival. And the man who had helped coordinate this impossible shift was about to see what his decision had truly unleashed. May 8, 1945, 3:02 p.m. A factory whistle sounds across an industrial valley in Ohio. Workers step away from control panels, from valves, from the constant hum that had defined their lives for nearly 3 years. Some remove gloves slowly, as if unsure what stillness feels like. Outside, Flags appear in windows. Radios crackle with announcements. The war in Europe is over. But inside the plant, reactors continue to run. Pipes still carry flow. Gauges remain steady. Because momentum, once created, does not simply stop. In a quiet office overlooking rows of steel vessels, William M. Jeffers reviews production reports no longer marked urgent. Output levels have surpassed every emergency projection. Facilities once built in haste now operate with methodical precision. What began as crisis response had matured into permanent capability. Jeffers does not speak. He simply studies the data. Thousands of tons produced, millions of components supplied, immeasurable miles traveled by machines that never halted for lack of material. You can almost sense the weight of realization settling into the room. This was never just about rubber. It was about whether a nation could redefine its limits under pressure. Across the United States, the industrial network forged during wartime remains intact. Plants that once symbolized emergency now represent possibility. The knowledge gained cannot be unlearned. The systems built cannot be erased. The world has changed, not only because of battles won, but because of constraints overcome. A resource once tied to geography had been liberated by chemistry and coordination. Dependence had been replaced by creation. And creation alters power more profoundly than conquest. In distant archives, military analysts assemble final reports examining the factors that sustained Allied mobility. They document production curves, logistical efficiencies, material durability. They trace the chain from seized plantations in Southeast Asia to continuous movement across continents. The conclusion emerges with quiet clarity. When a critical resource vanished, collapse did not follow. Innovation did. On battlefields long since silent, abandoned vehicles rest where they last moved. Tires weather slowly under open sky. Seals harden with time. Machines return to stillness. Yet the principle that kept them moving endures. War had forced industry to imagine the unimaginable, to build at a scale never attempted, at a speed never considered possible, under pressure no economy had ever faced. And it succeeded. Not perfectly, not easily, but decisively. Years later, historians would search for turning points in campaigns and conferences, in strategy rooms and frontline engagements. They would measure victories in territory, treaties, and timelines. But beneath those visible markers lay a quieter transformation, one that unfolded not with explosions, but with steady chemical reactions inside steel chambers. A transformation proving that when necessity reaches absolute urgency, imagination can become infrastructure. In the end, the most decisive weapon was not a machine, nor a commander, nor a battlefield maneuver. It was continuity, the ability to keep moving when movement seemed impossible, the ability to create supply when none existed, the ability to transform vulnerability into strength through sheer coordinated effort. And in that realization lies the true legacy of the synthetic rubber program, not simply that it sustained a war machine, but that it redefined what industrial society could achieve when survival demanded invention. The flow that began as a fragile experiment had become a permanent current in modern history. It never truly stopped.